Xavier Springer. He has total citations of 40 with H index 4 and ITED index 1. Beyond the renowned publication, he has two patents, in which one is at PCT worldwide and second one is Korean. He has worked on several projects and given 22 invited talks and 51 guest lectures. His professional membership include Indian Associations of Chemical Teachers, Chemical Research Society of India, Indian Science Congress Association, International EPR Society, Materials Research Society of India, and also appreciable great contributions to the college and society. Today, he is going to deliver his lectures on photocatalyst for water cleaning technology. Sir, I request you to deliver your valuable lectures and enlighten on this topic. Over to you, sir.
Thank you very much. Thank you very much, ma'am. Am I audible to you?
Yes, sir.
My slides are visible to you?
Yes, sir.
Please check whether my slides are getting changed or not. See, are they getting changed?
No, sir.
No. No.
Yes, sir.
Okay. Whether slides are getting changed or not?
But it is not on full screen.
Okay, okay. I will stop sharing and again entire screen share. I will go through entire screen. What could be done? I'm not able to share the entire screen here.
Kindly share your screen on 1 second.
Okay. Okay. Are you able to see the screen?
Yes, sir, I think
Yes, sir.
Is it working? Is it getting changed?
you
No,
can
sir.
easily do it. I request all the participants to, whenever lecture is going on, you may zoom it to visualize clearly.
खाली है ना प्लीज. स्क्रीन शेअर होत नाहीये.
झालं सर, झालं.
Sir, it's fine now. Okay, sir. Am I audible to you?
Yes, sir.
Hello.
Yes.
Yeah. Thank you very much, and sorry for inconvenience for about 20 minutes.
No problem, sir.
First of all, I would like to thank Honorable Principal Dr. Tandekar sir, Government Digvijay PG College, Rajnandgaon, Chhattisgarh, as well as Honorable Principal Dr. R.K. Iyer sir of New Arts Commerce and Science College, Parner, Head of the Department Dr. Beg sir, Dr. Reema madam, who has introduced very nicely, as well as all the participants. Thank you very much. The topic of presentation of my lecture is an efficient photocatalyst for water cleaning technology. Why it is necessary to have a water cleaning technology? Because if you just take a look at the global survey on the water quality, water is getting polluted day by day due to different pollutants. So because of the industrial development, large number of chemical, fine chemical, as well as other industries such as mining industries have been started, and many of the pollutants have been discharged into the water. So many of the toxic chemicals, they have been discharged into the water. Water is getting polluted, and it is becoming of no use for the drinking purpose as well as for the agricultural purpose. There are large number of organic compounds which are also discharged by the industries as a waste, and all these causes serious disorders and diseases. One of the class of these compounds is the endocrine disrupting chemicals. So if you just take a look at the global water quality, and hello,
Yes, sir.
am I audible to you all?
Yes, sir.
Yes, sir. Yes.
Yeah. So these are the facts which we will come to know from the global survey on water quality. 90% of sewage in developing countries is discharged without treating directly into the water bodies. Every day, 2 million tons of sewage and other effluents drain into the world's water. Particularly, industry discharges an estimated 300 to 400 megatons of waste into water bodies every year, and therefore water is getting polluted, and therefore there are certain issues in front of the world. Whole world is facing the water issues. And the major water problem, those are provision of safe drinking water, water requirements for further agricultural, hydroelectric, and industrial developments, sustainability of water development projects, as well as development of water resources shared by two or more states. We all know that there are many problems in the water resources which are shared naturally by the two or more states, as well as pollution of the water is very big problem. Although the topic is very big, I have put forth a limitation on my discussion. We are going to talk about the endocrine disrupting chemicals which are discharged into the water and how these are causing adverse effects, as well as what are the remedies to demineralize such endocrine disrupting chemicals. So what are endocrine disrupting chemicals? These are exogenous substances that behaves like hormones in the endocrine system and disrupt the physiologic function of endogenous hormones and causes adverse biological effects. These EDCs have been classified into different classes such as mimickers, blockers, triggers. Mimickers, they perform the same function, same chemical reactions like the natural hormones. Blockers, they are involved in the blocking of the cell receptors. They prevent naturally occurring hormonal activities. Triggers, they elicit unusual or abnormal reactions in the cells. And therefore, these EDCs have a strong influence on important regulatory growth homeostatic mechanisms inside our body, such as reproductive structure, maintenance of normal levels of glucose and minerals in blood, as well as control of body metabolism and blood pressure, and the other muscle as well as nervous system functions inside the body. And therefore, it is very necessary to remove them. So how these endocrine disrupting chemicals are discharged into the water resources? They are discharged into the water resources through their applications. So products associated with plastics, bisphenol is one of them that is discharged through the exhaustive use of plastic. Industrial chemicals such as chloro and nitrophenols, polychlorobenzenes and polybromobenzenes. Many dyeing agents such as methylene blue, bromothiamine blue. Pesticides such as monocrotophos, carbofuran, 2,4-D, and other organochlorine as well as organophosphorus pesticides. And pharmaceuticals which causes adverse effects such as diethylstilbestrol, which is synthetic hormonally active drug, as well as through household applications of the products such as synthetic detergents, EDCs such as nonylphenol and octylphenol, they are discharged into the water. And what are the consequences of these chemicals, these materials? These are organic pollutants. They produce hormonal response, and therefore they interfere with natural processes that regulate metabolic and physiological functions in our body. Even though if they are present in a trace quantities, they causes systemic effects as well as adverse effects. And these are persistent organic pollutants. Therefore, it is necessary to remove them, because if they are not removed, they causes birth defects, and therefore it is very necessary to take the care of our next generation. Therefore, if you look at all these consequences, we feel that it is very necessary to remove these endocrine disrupting chemicals. And as far as we all chemistry peoples are concerned, the whole world is expecting from us to suggest the remedies for the betterment of the life of human being on the surface of the earth crust. So there are certain methods available for the wastewater treatment for the removal of endocrine disrupting chemicals. They have been generally classified into three classes: physical, chemical, and biological methods. Physical methods are mainly based on the phenomenon of adsorption. Chemical methods are mainly based on the phenomenon of precipitation, ion exchange, ozonation, Penton's process, and some other processes. Biological methods such as activated sludge treatment, anaerobic as well as aerobic degradation processes. But these methods are having certain disadvantages, and therefore these methods does not demineralize the endocrine disrupting chemicals completely, and therefore the water quality is not maintained. So what are the disadvantages of the existing wastewater treatment technologies? All these technologies require further treatment or disposal. All these methods cannot result into a complete mineralization, that is, incomplete mineralization of the parent and intermediate pollutants is observed, and therefore it is necessary to find out as well as apply newer methods. Biological methods are there, but the biological methods are very slow as well as the results incompletely. Biodegradation is one of them, which is inactive for high concentration of the endocrine disrupting chemicals, and therefore we need a versatile method which will remove as well as demineralize as well as break down all these chemicals, although they are present in a very smaller quantities as well as they are present in a larger quantities. And photocatalysis is one of the viable method for the degradation of these persistent organic pollutants, and it is applicable for several environmental cleaner processes. It does not require a further treatment because it brings about a complete mineralization of the pollutants in aqueous medium, and therefore photocatalysis is the advanced oxidation technology which is carried out by using semiconductor materials which can be easily recycled, and therefore the cost of the process will be minimized. So which are the semiconductor materials which can be used as a photocatalyst? Those are available with us. They are titania, zinc oxide, tungsten oxide, zinc sulfide, cadmium sulfide, alpha Fe2O3, and strontium titanate. Out of all these, TiO2 is very important as it is biologically and chemically inert, as well as it is resistant to the photo corrosion as well as chemical corrosion. And the most important advantage of TiO2 in these technologies is that it is inexpensive. So the cost of process becomes very less. Another inexpensive photocatalyst is zinc oxide, which is a suitable alternative to TiO2. But the most important drawback is that it is unstable with respect to the incongruous dissolution to yield zinc oxide. Whenever zinc oxide particles are used, the zinc hydroxide is formed. Therefore, catalyst inactivation occurs, and therefore catalyst could not be recovered, could not be recycled, and therefore cost of the production increases. At the same time, the products of zinc, they are toxic to the living organisms, and therefore TiO2 has received great attention for environmental remediation. And therefore in our talk we are going to talk on TiO2 photocatalyst. So this is the mechanism where TiO2 is used as a photocatalyst, and photocatalysis occurs on the surface of a TiO2 catalyst. TiO2 produces cations, H plus ions, by the oxidation, as well as electrons are liberated. These electrons will bring about the reduction of the organic pollutants, as well as these protons, or which are usually called as holes, they will bring about the oxidation. And therefore, whenever UV light is made incident on these materials, excitation will occur, holes and electrons are produced. Electrons will bring about the reduction, holes will bring about the oxidation of the pollutant. Therefore, this technology is very useful, but the most important aspect of this technology is the electron hole recombination rate. If you look at the TiO2 material, nascent TiO2 material, as the band gap is there and the rate of electron hole combination is more, the electrons are not made available for the reduction as well as oxidation. Therefore, minimizing electron hole recombination rate of this TiO2 photocatalyst is the most important challenge, and this challenge can be made by modifying the TiO2 materials by converting it into nanocomposite material. So this side also shows that whenever the light is made incident on the surface of TiO2 material, holes and electrons are produced. Electrons brings about the reduction, holes brings about the oxidation of the organics. Thereby, organic materials are broken down or decomposed into CO2 and H2O. And this slide shows that if you try to coat these TiO2 nanoparticles on the surface of light storing material, light storing phosphor material, these materials can be used for the days and nights together. Otherwise, if you do not have any light storing source, our materials will be useful in the sunlight only. So that limitation can be overcome by making these TiO2 nanocomposites, by supporting them with light storing materials. So these are the different applications of TiO2 materials in the air purification, in the deodorization, in the soil proofing, in the sterilization, as well as in the water purification. And the most important is the water purification for all this. We already stated that there are certain disadvantages of these existing water cleaning technologies. Although we are making use of semiconductors, but whenever we are making use of bulk semiconductors, they are associated with limitations such as they have less surface area, they have fast electron hole recombination rate. As the surface area is less, they shows less adsorption property, and the band gap is high, and therefore we are unable to utilize the visible light, because in our sunlight almost 95% is the visible light and 5% of the light is UV light. As well as these bulk materials undergoes non-uniform dispersion of the dopant materials if they are supposed for the doping, and these dopant materials, they are separated out in the photocatalytic reaction from the surface of TiO2 material. And therefore, instead of making use of bulk semiconductor materials, nano semiconductor materials can be used because of the quantum size effect. They have reduced electron hole recombination rate. They have increased surface area, because of which adsorption properties increased, and therefore large number of pollutant molecules are adsorbed on the surface of the catalyst, as well as due to the modification of the material electrochemical properties, they can be tuned, and therefore materials can be used for the visible light adsorption. So how these materials can be obtained, can be synthesized? We already stated that they have high chemical stability, non-toxicity, high photocatalytic reactivity. Biologically and chemically they are inert. They are resistant to photocorrosion as well as chemical corrosion, as well as inexpensive, and therefore TiO2 has received a great attention for the environmental remediation. But still it is having certain limitations, and we are going to overcome these limitations through development of a new photocatalyst. So our main objective is to develop a new photocatalyst with the reduced particle size, which will have a quantum size effect, which will have reduced band gap energy, which will work under UV as well as visible light, and which will have increased surface area for the enhanced adsorption of the pollutant, and thereby it will improve the photocatalytic reactivity. And in order to prepare these new photocatalysts, doping materials as well as supporting materials such as transition metal oxides or certain other metal oxides can be used. And these are the methods which are usually available for the synthesis of nano TiO2 material through the solution route as well as gas phase route. We are mainly interested in the sol gel process because this method is having most important advantage is that even in our college laboratory, by just making use of a stirrer as well as a beaker as well as a magnetic needle, we will be able to carry out this sol gel process, and we will be able to carry out sol gel synthesis of the TiO2 nanoparticles. So high cost equipments are not required for this process. Room temperature, this process can be carried out at room temperature as well as under atmospheric conditions. This process can be carried out in a batch as well as continuous manner. Precursors which are used for the synthesis of materials, they can be finely dispersed, and therefore morphology of the nanoparticles can be controlled as well as their agglomeration can be controlled, and the nanoparticles of the desired size can be obtained through control of the stoichiometric proportions. Therefore, high purity as well as homogeneous nanoparticles can be obtained. So, what is the need for use of support or dopant in the TiO2 nanoparticles? Because nano TiO2 or the nascent TiO2 particles are having high electron hole recombination rate, band gap is very high, and therefore if you just make use of a support or a metal dopant, the dopant material or support material may have an intermediate level between the valence band and the conduction band, and therefore the energy gap will be reduced, band gap will be minimized, therefore electron hole recombination rate can be minimized, and therefore the electrons will be made available as well as protons or holes are also made available for reduction as well as oxidation technology respectively. Whenever we make use of a support, the particle size of the nanoparticles is controlled, and therefore nanoparticles with the high surface area can be obtained for the efficient adsorption of the pollutant material. Therefore, support or metal dopant can be used in these synthesis of materials. Such materials can be synthesized by using various technologies such as incipient, weight impregnation method, co-precipitation method, sol gel process. We are interested in the sol gel process. We already stated that why it is necessary to use the support in TiO2 material. So we have stated that solar energy contains about 4 to 5% of UV light, while the remaining 95% of light is visible light. And we must make use of this visible light properly. And therefore, it is necessary to develop a visible light active photocatalyst. These photocatalysts should be able to demineralize the water pollutants in the visible light mostly. And therefore, transition metal dope TiO2 can be used for the visible light photocatalysis. And these transition metal dopants could be cationic dopants, anionic dopants, or certain oxides which can be used as a support, which can be prepared by using a very low cost, inexpensive method, that is sol gel process. And in our method, we are going to use phosphor materials as a support for the preparation of a supported TiO2 nano photocatalyst. So the scope of the present work is the photocatalytic degradation of methylene blue with TiO2 in a batch type of slurry reactor. So in this process, what we have carried out, the work is photocatalytic degradation using commercial sample available in the market. We have prepared the material TiO2 photocatalyst by using phosphor material, calcium aluminate phosphor material as a support, and optimize the reaction parameters for the high degradation efficiency, as well as successfully we have applied a sol gel method for the synthesis of supported TiO2 photocatalyst. The materials which are synthesized have been characterized by using battery of techniques such as XRD, surface area measurement, by using BET method, FTIR, UV visible, SEM, TEM, as well as the photocatalytic efficiency is carried out by using experiment specially designed. Evaluation of photocatalytic activity of a pristine and phosphor supported TiO2 material in the degradation of methylene blue in a batch type or slurry type of batch type slurry reactor under UV radiation, and the comparison of the performance of TiO2 with the commercial TiO2 in the degradation and mineralization of the organic pollutants. So in a very simple way, the TiO2 supported TiO2 can be synthesized. Most of our laboratories are having titanium isopropoxide, as well as this calcium aluminate phosphor material is available, which can be doped with europium, dysprosium, as well as neodymium. And the photocatalysts which are utilized in this process, they are a commercial sample Degussa P25 TiO2, nano TiO2 sample which is prepared by the same method, as well as phosphor supported TiO2 material. And the model pollutant which is used is methylene blue. And this slide shows the experimental method for the preparation of this nano TiO2 material. So phosphor material is dispersed in ethanol, and acidic conditions are maintained by use of solution of acetic acid, and then a precursor material, that is titanium isopropoxide, is added in a variable quantities. Along with the stirring, TiO2 nanoparticles are obtained, which are dried at about 70 degrees Celsius for about 48 hours, and then they are subjected for the heat treatment at about 400 degrees Celsius for 3 hours, as well as 500, as well as 600. The reaction conditions, they are optimized, and the obtained materials were characterized by using different techniques. And the results and results which are obtained, they have been proposed over here as well as analyzed. So this slide shows the XRD studies on TiO2 nanoparticles. So the TiO2 nanoparticles were synthesized. Pristine TiO2 nanoparticles were synthesized in a laboratory by using salt gel method, and these are sintered at about 400 to 600 degrees Celsius in order to understand the stability of the phase which are present. Usually TiO2 is crystallized in a anatase as well as rutile phase. At a low temperature, anatase phase is stable, whereas whenever sintering temperature is increased, the transformation from anatase to rutile phase occurs. Usually it starts at about 450 degrees centigrade. These phases, they have been identified by using GCPD's database. The lattice parameters are calculated by using this XRD spectra, and the particle size is obtained by using Debye-Schreier equation. DC is equal to K lambda divided by beta cos theta. So this slide shows the XRD pattern, and at about 600 degrees Celsius, the anatase phase is evident. Therefore, at about 600 phase, rutile phase is evident, and therefore we have to think about the sintering temperature. Anatase phase is suitable for the demineralization, whereas rutile phase is not suitable, and therefore we want a material only with the anatase phase, and therefore we have to think about the sintering temperature, the temperature at which only anatase phase will be there will not be a rutile phase. So with this, we have finalized a sintering temperature. This is something regarding rutile and anatase phase, how they are crystallized. Rutile phase is having slight distortion from orthorhombic structure, and the unit cell therefore is stretched beyond a cubic cell. Whereas anatase phase shows distortion of the cubic lattice, which is more significant, and thus the resulting symmetry is less orthorhombic. In a previous slide, we have seen XRD of pure TiO2 materials, whereas this slide shows XRD of a phosphor supported TiO2 nanoparticles. The most important thing is that if you sinter at about 600 degrees Celsius, there is no evidence of the rutile phase. That means because of the presence of a phosphor material, TiO2 nanoparticles are remaining in exclusively anatase phase, and that is very important. Therefore, the advantage of this phosphor support is they gives the thermal stability to the material. So from these various peaks, it is clearly indicated that the material is crystalline in nature, and by using XRD we can find out the crystallite size, and phosphor supported TiO2 materials are having crystallite size ranging from 15 nanometer to about 25 nanometer. So these are more materials which are synthesized and sintered to about 400 to 600 degrees Celsius. So various compositions have been prepared by changing the concentration of Ti.
Hello.
Hello?
Hello. Yeah, this is Dr. Pramod Kumar Gavel from Kirodimal College, Raigad.
Yeah.
So can I ask one question?
Yeah, please.
So for this photocatalysis, so your anatase phase is responsible mainly?
Yeah.
Okay. So can you tell about TGA data of at 600 degrees centigrade? What is that? Have you done TGA?
No, sir, we haven't done TGA for these materials.
Okay. So
Yeah.
it is stable at 600 degrees centigrade?
Yeah, because see here, what I have shown you, we
Yeah.
have gone up to 600 degrees Celsius, and
Okay.
still there is no evidence of a rutile phase. There is only anatase phase. Whereas if you go for pristine TiO2 materials, which are synthesized by using same method, we can call it as a control method. If you look at 300, 400, 450 degrees Celsius, there is a slight indication of a rutile phase. And at 600 degrees Celsius, the picture clearly indicates that there is a rutile phase.
Yeah, so
So
600 degree.
for
It
pristine
is
material,
okay.
there is a rutile phase which is crystallized at about 600 degrees Celsius, whereas for nano TiO2 material, so I'm sorry, phosphor supported nano TiO2 material, at 400 degrees Celsius, there is no rutile phase, as well as at 600 degrees Celsius, there is no rutile phase. Rutile phase starts beyond 750 degrees Celsius in these materials. So we have optimized the sintering temperature in these materials, right?
Oh.
Okay. So this slide shows the 2 theta values, and the 2 theta value shows a shift, and this shift is clearly indicative of the presence of the bonding interactions between the phosphor support and TiO2 materials. This is evident from the infrared spectroscopic studies of the phosphor supported TiO2 materials. If you look at the slide, the infrared spectra of the pristine TiO2 material, phosphor material, as well as phosphor supported TiO2 material is mentioned. In the inset, we have mentioned all the three. So it is clearly visible that TiO-Ti bond absorption peaks, they are present in the region of 400 to 600 degrees Celsius for free TiO2. This is present at 543, whereas in phosphor supported TiO2 material, it is found to be shifted to 634 centimeter inverse. This indicates that TiO2 particles are not only adsorbed on the surface of the phosphor material. They have bonded chemically on the surface of the phosphor material, and therefore during the photocatalysis, these bonds could not be broken.
Photocatalysis नव्हे का?
तो सोपं आहे आणि त्याच्यावर
Photocatalyst वर
Hello? Would you like to ask anything? Hello? So the inference is that TiO2 nanoparticles are covalently bonded to the phosphor support material. This is also observed in the UV visible spectra of all these materials. There is red shift in the wavelength indicates that the band gap is reduced. One of the important expectation we have kept during the project is that we want material with the reduced band gap. So due to the use of phosphor support, the band gap is reduced, as well as TiO2 nanoparticles are chemically bonded on the surface of the material. There is no evidence for the anatase phase. There is no evidence for the rutile phase at about 600 degrees Celsius. And therefore, what we can say, our aims are satisfied in synthesizing the photocatalytic materials, which should be nanoparticles, which should be tunable for the visible light absorption, as well as which should have increased surface properties, surface area, so that absorption will be increased. So band gap is calculated by using UV visible. Now, if you look at the surface properties of the materials, so SCM and TM studies have been carried out on free as well as supported TiO2 nanocomposite materials. Slide picture A shows free TiO2 materials, as well as picture B and C shows the SEM images of phosphor supported TiO2 materials, which clearly indicates that there is a aggregation of the TiO2 nanoparticles on the surface of a phosphor material. There is a dispersion and higher degree of aggregation, which may be because of the chemical interactions between the phosphor surface and the TiO2 nanocrystallites. This slide shows the TM images.
And hello.
Hello?
Sorry for disturbing you.
Yeah.
So what is the size of that you supported on phosphorus material? Phosphor material?
Hello?
Yeah. So can you tell the size of that material?
Nanoparticles.
Yeah, on the surface of phosphor material.
Yeah.
It
It
is
is about,
aggregated. It
yeah.
is aggregated. You are saying
Yeah.
on the surface of phosphor material.
Yeah, it
So
is
can you
about,
tell this? Yeah.
it is about 8 to 15 nanometer.
8 to 50 and previous one?
Yeah. We can find out by using TM images, right?
Oh, yeah.
Yeah, so it is mentioned over here. There is dispersion as well as aggregation of the TiO2 material. And if you look into this slide, into this picture, there is a aggregation as well as what we have stated. The TM micrographs clearly indicates that the particle size is decreased due to the chemical interactions between the phosphor material and the TiO2 material, and is of about 8 to 15 nanometer.
So
We come
this was my question.
Yeah,
After
please.
aggregation, the particle size is decreased or increased?
Particle size is decreased, sir.
Yeah. So that is why I am saying.
There is aggregation, but there is no growth in the particle size.
Yeah. So it should be decreased for better photocatalytic activity. As
Yeah,
you said previously, quantum confinement.
Yeah, it is that. So these are IQAC studies of the materials, and they clearly indicates that the presence of titanium as well as calcium, aluminum, that means the materials of our desire has been synthesized. Surface properties have been measured by using BET method, by using nitrogen adsorption and desorption method. And this slide shows the nitrogen adsorption and desorption isotherms, which clearly indicates that there is a surface area of the nanoparticles is improved. So textural and structural properties of the phosphor supported TiO2 material, which are evaluated by using this BET method, they are mentioned over here. The materials, various materials have been prepared. Average pore diameter of these materials is estimated using adsorption branch of the isotherm, and the average diameter is in the range of say 4.4 to 5.8 for this material. And finally, the photocatalytic degradation experiment has been carried out by using a photocatalytic reactor. This left-hand side picture shows the design of the reactor. There is an arrangement for the lamp as well as a quartz container or cell is used. There is an arrangement for the oxygen inlet as well as outlet, and magnetic stirrer has been placed. If you look at the picture, three various photocatalysts have been employed, and the methylene blue concentration which was kept was same. After some time, if you look at the color change, the color change is observed in the three photocatalytic reactors to the different extent. This indicates that the photocatalytic degradation efficiency of the three different catalysts will be different. This experiment is carried out in the dark as well as is carried out in absence of TiO2 materials, and we could get the very good photocatalytic degradation efficiency of one of our material, that is PST4E as well as PST4D material within a very shorter time we observed about 87% of the demineralization or degradation of the material. This could be the probable mechanism for the demethylation of the methylene blue. We haven't gone into the details, but this is a probable material. The important conclusions from this experiment, from this project, they are: phosphor-supported TiO2 nanoparticles have been successfully synthesized by using a simple, low-cost Solgen method. XRD studies showed the presence of TiO2 in anatase phase even at high temperature, and the particle size is found to be decreased. The nanocrystalline size of TiO2 is well known, as we know, for the improved photocatalysis. Phosphor-supported TiO2 shows excellent thermal stability to the anatase phase, and modification by phosphor retards the phase transition in TiO2 from anatase to rutile. Presence of covalent interaction results into absorption towards longer wavelength indicates the decrease in band gap energy. XRD, U visible, same analysis confirm the nanocrystalline nature of TiO2. Photocatalytic activity of phosphor-supported nano TiO2 materials have been established using degradation of methylene blue in a UV light. Phosphor-supported nano TiO2 exhibited higher photocatalytic activity than a commercial bulk TiO2 material, that is Degussa P25 sample. Photocatalytic oxidation is a feasible technique, therefore, for the treatment of wastewater treatment which contains organic pollutants. Characterization of these materials: phosphor-supported nano TiO2 employing bed surface area and XPS techniques to evaluate physical and chemical properties can be utilized. Optimization of the phosphor concentration in the phosphor-supported nano TiO2 synthesis is done. Optimization of reaction parameters for enhanced photogradation efficiency are carried out. Evaluation of the rate constants and rate degradation from the kinetic studies can be done, and photocatalytic activity of the phosphor-supported nano TiO2 will be studied under the visible light in the future work. The work is going on all these, and on the same material, we could get one worldwide patent as well as 2 important paper. I would like to thank the facilities which were provided by Korea Research Institute of Chemical Technology, South Korea, during 2008-2009. I was supported. Hello? I was very much supported by Korea Research Institute of Chemical Technology for my postdoctoral work during 2008-2009. I would like to thank the project coordinator, Professor Ho-Jin Ryu of the institute, as well as Korea Research Institute of Technology, Government of Korea Republic, as well as I would like to thank the organizers, today's organizers of the faculty development program, that is principal of the government Digvijay PG College, Rajnandgaon, as well as principal of New Arts, Commerce and Science College, Parner, as well as convener and coordinator of this FDP. Thank you very much. If you have any questions, please.
Thank you, sir. If anyone has any question, they can directly ask to Thube sir. Platform is open.
Yeah, thank you, Professor, for very nice lecture. So I have few more questions because I am a little bit curious about your photocatalysis work. So I belong from actually basically organic background. So I have one question. You have chosen methylene blue as a pollutant R.
Yeah.
So only one single dye you have shown in your work. So is there any reason for choosing only single dye, that methylene blue?
Say, demineralization of methylene blue is quite easy as compared to the other model pollutants. Therefore, we have chosen only methylene blue.
Okay, it is one kind of model pollutant for
Yeah.
your work. So one more question: is there any effect on dissolved oxygen if that catalyst is working via that oxidation process? So it is that is radical form is generating. So is there any effect on dissolved oxygen in any adverse effect? Actually, I am asking about that any adverse effect on dissolved oxygen in any kind of water if you will do any kind of photocatalysis. In generally, it is in open environment. It is not closed vessel. It is
Yeah,
open.
yeah, yeah.
It is open vessel. So it is
Yeah.
exchanging from environment. So such kind of experiment can be performed in closed vessel.
Yeah, yeah. Your question is very good. See, we have not carried out such a kind of work. We were just uh, looking at the development of the photocatalyst and
Yes.
photocatalytic efficiency. So we haven't checked what will be the O2 concentration in that
Okay.
reaction mixture.
Yeah. Is there any ratio between that pollutant and catalyst ratio? Like any millimole concentration in between of that ratio of your pollutant and catalyst?
Yeah, yeah, we have optimized that ratio. And I have already shown in the slide that uh, uh, when we make use of different concentration of the photocatalyst as well as different concentration of methylene blue, photocatalytic degradation efficiency is found to be changed. And because of which only we could get a patent on that.
Okay. Yeah. Okay. Thank you so much. Thank you for your lecture.
Thank you very much, sir. Thank you.
Thank you, sir. I think there is no more questions.
Sir, I have one question.
Please.
Yes, sir.
Is I am audible, sir?
Yes, sir.
Sir, myself Rakesh Nagtode from RTM in Nagpur University.
Yeah.
Sir, my question is that is there the only photodegradation of methylene blue is possible, adsorption is not possible on nanocomposite material like copper oxide, urea formaldehyde, or zinc oxide, urea formaldehyde?
Can you repeat your question, sir?
Uh, can we do adsorption of methylene blue on nanocomposites?
See, my question, my objective was very focused. We were interested in designing photocatalyst as well as evaluating its photocatalytic efficiency and using particularly TiO2 material.
Yeah.
So we worked in that direction only. We
Okay.
haven't worked on copper materials or some other complex materials.
Okay.
But it is possible. But it is possible.
Thank you, sir.
Thank you. Thank you very much.
Thank you, sir.
Thank you very much.
I think there is no more questions. Thank you, sir, for taking such an amazing session. It was full of content. This will help us a lot in our learning. The most valuable aspects of these sessions was semiconductor photocatalysis, advantage of nano semiconductor, development of new photocatalysis. All of you have mentioned above all comes under the sustainable development and green chemistry, which is the demand of today. Additionally, the many of researchers will take advantage of your lectures. And I would like to express our sincere thanks to Dr. Thube sir for giving excellent coverage. Please accept our thanks for a great presentation.
Thank
This
you very much.
program could not be completed without your specific expertise and generous support. Thank you once again on the behalf of Chemistry Department. Thanks to everyone who attended these sessions for their valuable time and contributions. Now, I would like to tell you about tomorrow's schedule. Tomorrow's speaker is Dr. Manmohan Satnami sir and will give lectures on nanomaterial based free donor accepted payers for sensing applications. Once again, thanks to all. Now, I would end the session here. See you tomorrow. Thank you.
Thank you
Thube
very
sir,
much.
thank you very much.
Thank you very much,
This
sir.
FDP program was not possible without your support.
Thank you, sir. Thank you,
Thank
sir.
you very much, sir.
Our Digikar sir has initiated, sir, all these things. Thank you very much to all of you as well as Digikar sir.
Thank you,
Thank you,
sir.
sir.
Must lecture, very